नमस्कार. नमस्कार. Gravity. In physics, gravity from Latin gravitas, weight, is a fundamental interaction which causes mutual attraction between all things with mass or energy. Gravity is by far the weakest of the four fundamental interactions, approximately 10 per power 10 power sorry 38 power over 10 times weaker than the strong interaction, 36 power over 10 times weaker than the electromagnetic force, and 29 power over 10 times weaker than the weak interaction. As a result, it has no significant influence at the level of subatomic particles. However, gravity is the most significant interaction between objects at the macroscopic scale, and it determines the motion of planets, stars, galaxies, and even light. On Earth, sorry, on Earth, gravity gives weight to physical objects, and the moon's gravity causes tides in the oceans. Gravity also has many important biological functions, helping to guide the growth of plants through the process of gravitropism and influencing the circulation of fluids in multicellular organisms. Investigation into the effects of weightlessness has shown that gravity may play a role in immune system function and cell differentiation within the human body. The gravitational interaction between the original gaseous matter in the universe allowed it to coalesce and form stars, which eventually condensed into galaxies. So gravity is responsible for many of the large-scale structures in the universe. Gravity has an infinite range, although its effects become weaker as objects get farther away. Gravity is most accurately Gravity is most accurately described by general theory of relativity proposed by Albert Einstein in 1915, which describes gravity not as a force but as the curvature of space-time caused by the uneven distribution of mass and causing masses to move along geodesic lines. The most extreme example of this curvature of space-time is a black hole, from which nothing, not even light, can escape once past the black hole's event horizon. However, for most applications, gravity is well approximated by Newton's law of universal gravitation, which describes gravity as a force causing any two bodies to be attracted toward each other with magnitude proportional to the product of their masses and inversely proportional to the square of the distance between them. Current models of particle physics imply that the earliest evidence instance of gravity in the universe, possibly in the form of quantum gravity, supergravity, or a gravitational singularity along with ordinary space and time, developed during the Planck epoch up to minus 43 power over 10 seconds after the birth of the universe, possibly from a primeval state such as false vacuum, quantum vacuum, or virtual particle in a currently unknown manner. Scientists are currently working to develop a theory of gravity consistent with quantum mechanics, a quantum gravity theory which would allow gravity to be united in a common mathematical framework, a theory of everything with the other three fundamental interactions of physics. History ancient world, the nature and the mechanism of gravity was explored by a wide range of ancient scholars. In Greece, Aristotle believed that all objects fell towards the earth because the earth was the center of the universe and attracted all of the mass in the universe towards it. He also thought that the speed of a falling object should increase with its weight, a conclusion which was later shown to be false. While Aristotle's view was widely accepted throughout ancient Greece, there were other thinkers such as Plutarch who correctly predicted that the attraction of gravity was not unique to the Earth. Although he did not understand gravity as a force, the ancient Greek philosopher Archimedes discovered the center of gravity of a triangle. He also postulated that if two equal weights did not have the same center of gravity, the center of gravity of the two weights together would be in the middle of the line that joins their centers of gravity. In India, the mathematician astronomer Aryabhatta first identified gravity to explain why objects are not driven away from the Earth by the centrifugal force of the planet's rotation. Later in the seventh century, Sri Brahmagupta proposed the idea that gravity is an attractive force which draws objects to the Earth and used the term Gurutvakarsan to describe it. In the in the ancient Middle East, gravity was a topic of fierce debate. The Persian intellectual Al-Biruni believed that the force of gravity was not unique to the earth, and he correctly assumed that other heavenly bodies should exert a gravitational attraction as well. In contrast, Al-Khazini held the same position as Aristotle that all matter in the universe is attracted to the center of the earth. Scientific revolution in the mid-16th century, various European scientists experimentally disproved the Aristotelian notion that heavier objects fall at a faster rate. In particular, the Spanish Dominican priest Domingo de Soto wrote in 1551 that bodies in free fall uniformly accelerate. De Soto may have been influenced by earlier experiments conducted by other Dominican priests in Italy, including those by Benedetto Verci, Francesco Beato, Luca Ghini, and Giovan Bellaso, which contradicted Aristotle's teachings on the fall of bodies. In sorry, the mid-16th century Italian physicist Giambattista Benedetti published papers claiming that due to specific gravity, objects made of the same material but with different masses would fall at the same speed. The mid-16th century Italian physicist Giambattista Benedetti published papers claiming that due to specific gravity, objects made of the same material but with different masses would fall at the same speed. With the 1586 Delft Tower experiment, the Flemish physicist Simon Stevin observed that two cannonballs of differing sizes and weights fell at the same rate when dropped from a tower. Finally, in late 16th century, Galileo Galilei performed his famous Leaning Tower of Pisa experiment in order to show once again that balls of different weights would fall at the same speed. Combining this knowledge with careful measurements of balls rolling down inclines, Galileo firmly established that gravitational acceleration is the same for all objects. Galileo postulated that air resistance is the reason that objects with a low density and high surface area fall more slowly in an atmosphere. In 1604, Galileo correctly hypothesized that the distance of a falling object is proportional to the square of the time elapsed. This was later confirmed by Italian scientists Jesus Grimaldi and Riccioli between 1640 and 1650. They also calculated the magnitude of the Earth's gravity by measuring the oscillations of a pendulum. In 1604, Galileo correctly hypothesized that the distance of a falling object is proportional to the square of the time elapsed. This was later confirmed by Italian scientists Jesus Grimaldi and Riccioli between 1640 and 1650. They also calculated the magnitude of the Earth's gravity by measuring the oscillations of a pendulum. Newton's theory of gravitation. In 1684, Newton sent a manuscript to Edmond Halley titled De Motu Corporum in Chiron on the motion of bodies in an orbit, which provided a physical justification for Kepler's law of planetary motion. Halley was impressed by the manuscript and urged Newton to expand on it, and a few years later, Newton published a groundbreaking book called Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. In this book, Newton described gravitation as a universal force and claimed that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve. This statement was later condensed into the following inverse square law: F equals to G into m1 into m2 by r square, where F is the force m1 and m2 are the masses of the objects interacting, r is the distance between the centers of the masses, and g is the gravitational constant. This statement was later condensed into the following inverse square law: F equals to G into m1 into m2 by r square, where F is the force m1 and m2 are the masses of the objects interacting, r is the distance between the centers of the masses, and g is the gravitational constant. Newton's Principia was well received by the scientific community, and his law of gravitation quickly spread across the European world. More than a century later, in 1821, his theory of gravitation rose to even greater prominence when it was used to predict the existence of Neptune. In that year, the French astronomer Alexis Howard used this theory to create a table modeling the orbit of Uranus, which was shown to differ significantly from the planet's actual trajectory. In order to explain this discrepancy, many astronomers speculated that there might be a large object beyond the orbit of Uranus which was disrupting its orbit. In 1846, the astronomers John Couch Adams and Irving Lee Warrior independently used Newton's law to predict Neptune's location in the night sky, and the planet was discovered there within a day. General relativity. Eventually, astronomers noticed an eccentricity in the orbit of the planet Mercury, which could not be explained by Newton's theory. The perihelion of the orbit was increased by about 42.98 arc seconds per century. The most obvious explanation for this discrepancy was an as yet undiscovered celestial body such as a planet orbiting the sun even closer than Mercury, but all efforts to find such a body turned out to be fruitless. Finally, in 1915, Albert Einstein developed a theory of general relativity which was able to accurately model Mercury's Mercury's orbit. In general relativity, the effects of gravitation are ascribed to space-time curvature instead of a force. Einstein began to toy with this idea in the form of the equivalence principle, a discovery which he later described as the happiest thought of my life. In this theory, free fall is considered to be equivalent to inertial motion, meaning that free falling or inertial objects are accelerated relative to non-inertial observers on the ground. In contrast to Newtonian physics, Einstein believed that it was possible for this acceleration to occur without any force being applied to the object. Einstein proposed that spacetime is curved by matter and that free-falling objects are moving along locally straight paths in curved spacetime. These straight paths are called geodesics. As in Newton's first law of motion, Einstein believed that a force applied to an object would cause it to deviate from a geodesic. For instance, people standing on the surface of the earth are prevented from following a geodesic path because the mechanical resistance of the earth exerts an upward force on them. This explains why moving along the geodesics in space-time is considered inertial. Einstein's description of gravity was quickly accepted by the majority of physicists as it was able to explain a wide variety of previously baffling experimental results. In the coming years, a wide range of experiments provided additional support for the idea of general relativity. Today, Einstein's theory of relativity is used for all gravitational calculations where absolute precision is desired. Although Newton's inverse square law continues to be a useful and fairly accurate approximation, modern research in modern physics, general relativity remains the framework for the understanding of gravity. Physicists continue to work to find two solutions to the Einstein's field equations that form the basis of general relativity. While some scientists have speculated that general relativity may not be applicable at all in certain scenarios, Einstein field equations The Einstein field equations are a system of 10 partial differential equations which describe how matter affects the curvature of space-time. The system is often expressed in the following simplified form: G micro V plus AG micro V equals to 8 into pi into G into T micro V by 4 power over C, where G micro V is the Einstein tensor. G mic- capital G where sorry capital G micro V is the Einstein tensor. Small g micro V is the metric tensor. Capital T micro V is the stress energy tensor. A is the G cosmological constant. Sorry. Sorry. Einstein field equations. The Einstein field equations are a system of 10 partial differential equations which describe how matter affects the curvature of spacetime. The system is often expressed in the following simplified form: G mu nu plus lambda. G mu nu equals to 8 pi G into T mu nu by 4 power over C, where capital G mu nu is the Einstein tensor, small g mu nu is the metric tensor, T mu nu is the stress energy tensor, lambda is the cosmological constant, G is Newton's gravitational constant, and C is the speed of light. The term 8 into pi into G by 4 power of C is sometimes referred to as the Einstein's gravitational constant. kappa. A major area of research is the discovery of exact solutions to the Einstein field equations. Solving these equations amounts to calculating a precise value for the metric tensor which defines the curvature and geometry of spacetime under certain physical conditions. There is no formal definition for what constitutes such solutions, but most scientists agree that they should be expressible using elementary functions or linear differential equations. Some of the most notable solutions of the equations include the squared, squa- sorry, Schwarzschild solution, which describes spacetime surrounding a spherically symmetric, non-rotating, uncharged massive object for compact enough objects. This solution generated a black hole with a central singularity 8 points far away from the central mass. The accelerations predicted by the Schwarzschild solution are practically identical to those predicted by Newton's theory of gravity. The Reijner-Nordstrom solution, which analyzes a non-rotating spherically symmetric object with charge and was independently discovered by several different researchers between 1916 and 1921. In some cases, this solution can predict the existence of black holes with double event horizons. The Kerr solution, which generalizes the Schwarzschild solution to rotating massive objects because of the difficulty of factoring in the effects of rotation into Einstein's field equations. This solution was not discovered until 1963. The Kerr-Newman solution for charged rotating massive objects. This solution was derived in 1964 using the same technique of complex coordinate transformation that was used for the Kerr solution. The cosmological Friedmann-Lemaitre-Robertson-Walker solution discovered in 1922 by Alexander Friedmann and then confirmed in 1927 by George Lemaitre. This solution predicts the expansion of the universe, and 7 years after its publication, Edwin Hubble measured this expansion for the first time. It even showed that general relativity was incompatible with a static universe, and Einstein later considered that he had been wrong to design his field equations to account for a universe that was not expanding. Today there remain many important situations in which the Einstein field equations have not been solved. Chief among these is the two-body problem, which concerns the geometry of spacetime surrounding two mutually interacting massive objects such as the Sun and the Earth, or the two stars in a binary star system. The situation gets even more complicated when considering the interactions of three or more massive bodies, the n-body problem, and some scientists suspect that the Einstein field equations will never be solved in this context. However, it is still possible to construct an approximate solution to the field equations in the n-body problem by using the technique of post-Newtonian expansion. In general, the extreme nonlinearity of Einstein's field equations makes it difficult to solve them in all but the most specific cases. Gravity and quantum mechanics. An open question is whether it is possible to describe the small-scale interactions of gravity with the same framework as quantum mechanics. General relativity describes large-scale bulk properties, whereas Quantum mechanics is the framework to describe the smallest scales interactions of matter without modifications. These frameworks are incompatible. One path is to describe gravity in the framework of quantum field theory, which has been successful to accurately describe the other fundamental interactions. The electromagnetic force arises from an exchange of virtual photons, where the QFT description of gravity is that there is an exchange of virtual gravitations. There is an exchange of virtual gravitations. This description reproduces general relativity in the classical limit. However, this approach fails at short distances of the order of the Planck length, where a more complete theory of quantum gravity or a new approach to quantum mechanics is required. Tests of general relativity. It is difficult to test the theory of general relativity on Earth because of small masses and velocities. Its predictions are almost identical to that of Newtonian gravity. Still, since its development, an ongoing series of experimental results have provided support for the theory. In 1919, the British astrophysicist Arthur Eddington was able to confirm the predicted gravitational lensing of light during that year's solar eclipse. Eddington measured starlight reflections twice, those predicted by Newtonian corpuscular theory in accordance with the predictions of general relativity. Although Eddington's analysis was later disputed, this experiment made Einstein famous almost overnight and caused general relativity to become widely accepted in the scientific community. In 1959, American physicists Robert Pound and Glenn Rebka performed an experiment in which they used gamma rays to confirm the prediction of gravitational time dilation. By sending the rays down a 74-foot tower and measuring their frequency at the bottom, the scientists confirmed that light is red-shifted as it moves towards a source of gravity. The observed redshift also supported the idea that time runs more slowly in the presence of a gravitational field. In the presence of a gravitational, sorry, the observed redshift also supported the idea that time runs more slowly in the presence of a gravitational field. The time, sorry, the time delay of light passage close to a massive object was first identified by Irwin I. Shapiro in 1964 in interplanetary spacecraft signals. In 1971, scientists discovered the first ever black hole in the galaxy, Cygnus. The black hole was detected because it was emitting bursts of X-rays as it consumed a smaller star, and it came to be known as Cygnus X1. This discovery confirmed yet another prediction of general relativity because Einstein's equations implied that light could not escape from a sufficiently large and compact object. General relativity states that gravity acts on light and matter equally, meaning that sufficiently massive a sufficiently massive object could warp light around it and create a gravitational lens. This phenomenon was observed for the first time in 1979 when the Hubble telescope shot two minor images of the same quasar whose light had been bent around the galaxy YGKOWG1 frame, dragging. The idea that a rotating massive object should twist spacetime around it was confirmed by gravity probe B results in 2011. In 2015, the LIGO observatory detected faint gravitational waves, the existence of which had been predicted by general relativity. Scientists believe that the waves emanated from a black hole merger that occurred 1.5 billion light years away. In 2015, the LIGO Observatory detected faint gravitational waves, the existence of which had been predicted by general relativity. Scientists believe that the waves emanated from a black hole merger that occurred 1.5 billion light years away. Specific, specific, specifics Earth's gravity. Every planetary body, including the Earth, is surrounded by its own gravitational field, which can be conceptualized with Newtonian physics as exerting an attractive force on all objects. Assuming a spherically symmet- sorry, spherically symmetrical planet, the strength of this field at any given point above the surface is proportional to the planetary body's mass and inversely proportional to the square of the distance from the center of the body. The strength of the gravitational field is numerically equal to the acceleration of objects under its influence. The rate of acceleration of falling objects near the Earth's surface varies very slightly depending on latitude, surface features such as mountains and ridges, and perhaps unusually high or low subsurface densities. For purposes of weights and measures, a standard gravity value is defined by the International Bureau of Weights and Measures under the International System of Units (SI). The force of gravity on Earth is the resultant vector sum of two forces: the gravitational attraction in accordance with Newton's universal law of gravitation, and b. the centrifugal force, which results from the choice of an earth-bound rotating frame of reference. The force of gravity is weakest at the equator because of the centrifugal force caused by the Earth's rotation, and because points on the equator are farthest from the center of the Earth. The force of gravity varies with latitude and increases from about 9.780 meter per second square at the equator to about 9.832 meter per second square at the poles. Origin: the earliest gravity, possibly in the form of quantum gravity, supergravity, or a gravitational singularity along with ordinary space and time, developed during the Planck epoch up to minus 43 power over 10 seconds after the birth of the universe, possibly from a primeval state such as false vacuum, quantum vacuum, or virtual particle in a currently unknown manner. Gravitational radiation. General relativity predicts that energy can be transported out of a system through gravitational radiation. The first indirect evidence of gravitational radiation was through measurements of the Halsey-Taylor boundary in 1973. This system consists of a pulsar and neutron star in orbit around one another. Its orbital period has decreased since its initial discovery due to a loss of energy, which is consistent for the amount of energy lost due to gravitational radiation. This research was awarded the Nobel Prize in Physics in 1993. The first direct evidence for gravitational radiation was measured on 14th September 2015 by the LIGO detectors. The gravitational waves emitted during the collision of two black holes 1.3 billion light-years from Earth were measured. This observation confirms the theoretical predictions of Einstein and others that such waves exist. It also opens the way for practical observation and understanding of the nature of gravity and events in the universe, including the Big Bang, neutron star, and black hole formation, also create detectable amounts of gravitational radiation. This research was awarded the Nobel Prize in Physics in 2007. Speed of gravity. In December 2012, a research team in China announced that it has produced measurements of the phase lag of Earth tides during full and new moons, which seem to prove that the speed of gravity is equal to the speed of light. This means that if the Sun suddenly disappeared, the Earth would keep orbiting the vacant point normally for 8 minutes which is the time light takes to travel that distance. The team's findings were released in the Chinese Science Bulletin in February 2013. In October 2017, the LIGO and Virgo detectors received gravitational wave signals within 2 seconds of gamma ray satellites and optical telescopes seeing signals from the same direction. This confirmed that the speed of gravitational waves was the same as the speed of light. Anomalies and discrepancies. There are some observations that are not adequately accounted for, which may point to the need for better theories of gravity, or perhaps be explained in other ways. Extra-fast stars in galaxies follow a distribution of velocity. Extra-fast stars in galaxies follow a distribution of velocities, which where stars on extra-fast stars sorry sorry extra-fast stars in galaxies follow a distribution of velocities where stars on the outskirts are moving faster than they should according to the observed distribution of normal matter. Galaxies within galaxy clusters show a similar pattern. Sorry, dark matter which would interact through gravitation but not electromagnetically would account for the discrepancy. Various modifications to Newtonian dynamics have also been proposed. Flevi anomaly. Various spacetime craft. Very sorry. Various spacecraft have experienced greater acceleration than expected during gravity assist maneuvers. Accelerating expansion. The metric expansion of space seems to be speeding up. Dark energy has been proposed to explain this. A recent alternative explanation is that the geometry of space is not homogeneous due to clusters of galaxies, and that when the data are reinterpreted to take this into account, the expansion is not speeding up after all. However, this conclusion is disputed. Anomalous increase of the astronomical unit. Recent measurements indicate that the planetary orbits are widening faster than if this were also solely through the Sun losing mass by radiating energy. Extra energetic photons traveling through galaxy clusters should gain energy and then lose it again on the way out. The accelerating expansion of the universe should stop the photons returning all the energy, but even taking this into account, photons from the cosmic microwave background radiation gain twice as much energy as expected. This may indicate that gravity falls off faster than universe squared at certain distance scales. Extramassive hydrogen clouds. The spectral lines of the Lyman alpha forest suggest that hydrogen clouds are more clumped together at certain scales than expected, and like dark flow may indicate that gravity falls off slower than universe square at certain distance scales. Alternative theories. Historical alternative theories. Aristotelian theory of gravity. Lee-Sage's theory of gravitation 1784 also calls Lee-Sage gravity, but originally proposed by Fatio and further elaborated by George Louis Lee-Sage based on a fluid-based explanation where light gas fills the entire universe. Ritz, Ritz theory of gravitation and Chem Physics 13 145 1908 pp 267 to 271 Weber. Gauss electrodynamics applied to gravitation. Classical advancement of perihelia. Nordstrom's theory of gravitation 1912 1913, an early competitor of general relativity. Kaluza Green theory 1921. Whitehead's theory of gravitation 1922, another early competitor of general relativity. Modern alternative theories. Brans-Dicke theory of sorry sorry Brans Decay theory of gravity 1961, induced gravity 1967, proposed by Andrei Sakharov, according to which general relativity might arise from quantum field theories of matter, string theory late 1960s, FR gravity 1970, Horndeski theory 1974, supergravity 1976, in the modified Newtonian dynamics mode 1981, Mordechai Milgrom proposes a modification of Newton's second law of motion for small accelerations. The self-creation cosmology theory of gravity 1982 by G. A. Barber, in which the Brans-Dicke theory is modified to allow mass creation. Loop quantum gravity 1988 by Carlo Rovelli, Lee Smolin, and Abhay Astekar. Non-symmetric gravitational theory (NGT) 1994 by John Moffat. Tensor vector scalar gravity T-Waves 2004, a relativistic modification of Mond by Jacob Bekenstein. Chameleon theory 2004 by Justin Khoury and Amanda Weltman. Pre-Shuron theory 2013 by Olivier Minajoli and Aurélien Hayes. Conformal gravity as an entropic force, gravity arising as an emergent phenomenon from the thermodynamic concept of entropy. In the superfilled vacuum theory, the gravity and curved spacetime arise as a collective excitation mode of non-relativistic background superfluid massive gravity, a theory where gravitons and gravitational waves have a non-zero mass. See also anti-gravity, the idea of neutralizing or repelling gravity, artificial gravity, Gauss law of gravity, gravitational potential, micro-g environment, also called microgravity, Newton's law of motion, standard gravitational parameter, weightlessness equation for a falling body. Footnotes: Dict.cc Dictionary Gravitas English Latin translation archived from the original on 13th August 2011, arrived 11 September 2018. Krebs, Robert T. 1999. Scientific Development and Misconceptions Through the Ages, a reference guide, illustrated edition, Greenwood Publishing Group, P133, ISBN 978-0-313-30226-8. Hubble site, black holes, gravity. Gravity's relentless pull. Hubble site.org, archived from the original 26 December 2018, retrieved 7 October 2016. Staff Worth of the Universe, University of Oregon, archived from the original 28 November 2018, retrieved 24 September 2016. Discusses Planck time and Planck era at the very beginning of the universe. Cappy, Alberto, The Concept of Gravity Before Newton, Culture and Cosmos, Becker, Frederick Palmerino, Carla Rita, 1st June 2020, Motion to the Center or Motion to the Whole, Plutarch's view on gravity and their influence on Galileo. ISIS, ISIS, sorry, ISIS 1112-217-2 217-238. William Noel, 13th October 2011, the Archimedes Codex, revealing the secrets of the world's greatest palimpsest, Hecate, UKP 125, ISBN 978-1-78022-198-4, archived from the original on 7th January 2020, retrieved 10th April 2019. C.J. Tuplin, Lewis Wolpert, 2002. Science and Mathematics in Ancient Greek Culture, Hecate, UKP 11, ISBN 978-0-19-8152. 48-4, archived from the original on 17th January 2020, retrieved 10th April 2019. Pickover, Clifford, 16th April 2008. Archimedes to Hawking, Law of Science and the Great Mind minds behind them. Oxford University Press, ISBN 9780199792689, archived from the original 19th January 2017, retrieved 29th August 2017. Bose Manak Kumar, 1988, late classical India, M. Mukherjee and Co. Archived from the original 13th August 2011, archived 28th July 2011. Sin Amrati 2005, The Argumentative India, Ellen Lane, P29, ISBN 978-0-7139-9687-6, Star S. Frederick 2015, Lost Environment, Central Asia's Golden Age from the Arabs' Conquest to Tamerlane, Princeton University Press, P260, ISBN 978-069-1165-851, Rozhanskaya, Mariam Levinova, IS 1996, Statics in Rushdie Rashid edition, Encyclopedia of the History of Arabic Science, Volume 2, Psychology Press, pp. 614 to 642, ISBN 9780415124119, Wallace William, A. 2018-2004, Domingo de Soto, and the Early Galileo Essays on Introductory History, Abingdon, UK, Routledge, pp. 119, 121 to 122, ISBN 978-1-351-159 15959-3, archived from the original on 16th June 2011, retrieved 4th August 2011. Travkin I, 1963, the two versions of G.V. Benedict's Demonstratio Proportionum Mortum Localium ISIS 42259-262 DY 10.1086/34970 ISS ISSN 0021-1753 JS Store 228543 S2 CID 144883728 Shilling Govard 31st July 2017, Ripples in Space-Time, Einstein Gravitational Waves and the Future of Astronomy, Harvard University Press, p. 296, ISBN 9780674971660, archived from the original 16th December 2011, retrieved 16th December 2011, Balfield June 2005, Tall Tales, Nature News, DOI 10.1038/News 050613/10, Galileo 1638, 2 New Sciences, First Day, Salviati speaks. If this were what Aristotle meant, you would burden him with another error, which would amount to a falsehood, because since there is no such sheer height available on earth, it is clear that Aristotle could not have made the experiment, yet he wishes to give us the impression of his having performed it when he speaks of such an effect on one which we see. Gillespie, Charles Colston, 1960, The Age of Objectivity in an Essay in the History of Scientific Ideas, Princeton University Press, p. 326, ISBN 0-691-02350-6, J.L. Hellbron, Electricity in the 17th and 18th Century, A Study of Early Modern Physics, Berkeley University of California, 1979, 180, Sagan, Carl N. Drew, Ian, and 1987, Cosmet, New York, Random House, pp. 52 to 58, ISBN 978-0-307-01005-0, archived from the original 15th June 2011, retrieved 5th August 2011. The reception of Newton's Principia PDF, retrieved 6th May 2022. This month in Physics History, www.aps.org, retrieved 6th May 2022. Nobel Anna M. March 1986. The real value of mercury is very highly advanced. Nature 320. 6057 3941, Web code 1986, Nature 320 39, and DOI 10.3 10.1038/320039 AOS2 CID 4325839, Webjaw, Mewjo Dugan died on 23rd November 2015. Without Einstein, it would have taken decades longer to understand gravity. He died 21st May 2022. Gravity and warp distance spacetime. Black holes.org archived from the original on 21st June 2011. He died 16th October 2010. Swiss cheesy model of the cosmos is full of holes. Archived 6th May 2005 at the Wayback Machine Scientist issue 2678 18th October 2008. Sean Marcus 16th March 2009 Gravity May Venture Bare Matter Fear Fears to Tread New Scientist archived from the original on 18th December 2012 retired 4 August 2013 Barnes C.H. March 2014 Jordan Barnes Dyke Theory Scholarspedia 94315331358 ARXIVGR QC /020703 bib code 14 SCHPJ 93135 DY 10.4249 Scholarpedia dot 31358 or sorry Horndeski GW Space September 1974 second order scalar tensor field equations in a four-dimensional space International Journal of Theoretical Physics 88 103 63 to 384 Web code 1974 IJTP 10363 HQI 1010.1007 slash BF 018036 sorry 7638 has 2 CID 122346086 before 919 and for IJTP dot 10.3638 DY 10.1007 slash BF 01807638 has 2 CID 122346086 Milgrom M June 2014 The Mond Paradigm of Modified Dynamics Scholarpedia 9631410 Web code 2004 Web code colon sorry Web code colon scholar sorry Webcon sorry Web code colon 2014 SCHPJ dot 931410 MDOI colon 10.4249 slash scholarpedia dot 31410 Hodgen Mark P. Lammer Jhal C 2011 Einstein Gravity from conformal gravity ARXIV colon 1105.5632 Hep TH references Halliday David Robert Resnick references Halliday David Robert Resnick Kenneth S. Crane 2011 Physics V.1. New York colon John Wiley and Sons ISBN 197-0-471-32 057-9 Sherway Raymond A. Jewett John W. 2014 Physics for Scientists and Engineers 6th edition Brooks/Corley ISBN 978-0-534-40842-8 Tipler Paul 4 Physics for Scientists and Engineers Mechanics Observations and Waves Thermodynamics 5th edition W. H. Freeman ISBN 978-0-7167-0809-4 Further readings Thorneyke S. Misner Charles W. Wheeler John Archibald 1973 Gravitation W. H. Freeman ISBN 978-0-7167-0344-0 Panic Richard 2nd August 2019 Everything you thought you knew about gravity is wrong. Washington Post धन्यवाद। थैंक यू सो मच। धन्यवाद। थैंक यू so much।